If I can find the clicker, it's a little bit easier to show you. Leave it on. There it is. Okay. Click. So atomic radius, that's the size of the atom. The radius is just measuring the middle to the edge. For metallic radius here, again, you can measure from the nucleus to the nucleus. For covalent radius here, again, nucleus to the nucleus, and we're looking at two connected atoms. So it's 1/2 of the distance between two adjacent nuclei. So if you take this and divide it by 2, that's called the atomic radius. Now, the radius here, as you can see, which of these atoms here has the largest radius? Cesium. Okay. Now, what happens as you go down on the periodic table? It's bigger. So that's because more shells and subshells are being added, right? And the distance, the energy levels, as you go further and further on each shell or energy level, it's going to be further away from the nucleus. But as you go across, you see that it gets what? Smaller. And that's because there's a larger positive charge and there's more electrons around the outside. Both of those factors cause them to condense. Because neon, you got 10 positive, 10 negative. Very simple. They would attract more than 9 positive and 9 negative. Just in that simple model. Okay? So as you go down the periodic table, the radius increases. As you go across, the radius decreases. And this is true even for the noble gases over here. Atomic radius decreases across the periodic table to the right, and atomic radius increases as you go down the table. Again, this is the same way of showing the same exact thing I did on the last 2 slides. Different picture. If it works better for you, good. This here is the radius versus the atomic number. Okay? Now, this shows the radii of these particular elements. You'll notice the ones at the bottom are each the noble gases. They are the smallest in their effective periods. Which ones are the largest in their period? The alkali metals. Now, if you think of the alkali metals, they're largest in their period. How many electrons do they want to lose or gain? 1. They're really large. They've got an electron. Okay? It's kind of like this pen if it was worth $1,000. And I just held it out here. And I said, $1,000. Okay? Gone. It's further away from me. Now, if I get it back just by chance, which wouldn't happen in real life, and I was larger, much larger, and it was way out here, and it was really far away from me. Okay? It's pretty easy for someone to take that. It's pretty easy for someone to take that and lose that. So that's like an electron in a larger atom. All of these are larger compared to the rest in the row. So it's easier to take one from lithium and sodium, potassium, rubidium, and cesium in general because of the distance. They got less energy. Now, the atomic number, as you look across in one row, we're looking at row 3 here, period 3, sodium to argon. As you look across this graph, what do you see? Okay? Zeff increases, okay? Linear relationship. Atomic radius does what? Decreases. So the larger the Zeff, the what? Smaller the size. So that helps us. Okay? Now is atomic radius perfect with that pattern? No, there might be some other things going on. You got to consider that, but at this point we see the general pattern. As Zeff increases, the electrons are held with less force, thus they're further from the nucleus. Okay? And the Zeff also relates to shielding. Again, the shielding makes a difference because the electrons inside repel the electrons outside. Now, why is the atomic radius of potassium greater than calcium? Right? Why is that? So tell the person next to you why you think it is right now, just on your ideas, what you got. Ready to go? Just one opinion. Yes, sir. Yeah, more protons. More protons. There's a stronger pull. Good. Any other ideas on why that would be? Yeah. Okay. So less electrons and protons affected. Now, do they both have the same shielding? Yeah, they both got the same shielding. So the shielding isn't an issue in terms of both of these. Okay? So, K has this electron configuration. Okay? It's got 19 protons, 18 electrons in its shield, so its ZF is... That's really hard math. Oh yeah, +1, there we go. And then, calcium. ZF, 20 minus 18 is positive 2. Yeah, I know. That's the hardest math. I think we should spend more time doing this equation. You want me to slow down a little bit? Yeah. No, seriously. I mean, after you do like calculus, you're like, wait, do I? Fortunately, there's no negative numbers in here except subtraction. But yeah. So the cool thing is, though, ZF is larger, so that means the atom size is smaller. Cool. So potassium is greater than calcium because equal electron shielding. Calcium has one more proton than potassium. Thank you. Thank you. You guys were absolutely right. ZF is greater than the ZF for K. And calcium, outermost electron experience more attractive force towards the nucleus. The outermost electron experiences more attractive force because there's more positive protons in the middle. So this is just electrostatic interaction. The funny thing is, most of chemistry is explained with just the attraction between electrons and protons. That's it. You understand this here, you can explain most chemistry. So it's kind of like, oh, it's so basic, but it will show you some really cool things. So the next thing, cations. A cation is when an element, what with an electron? Loses an electron or 2 electrons or 3 electrons, or whatever the case may be. The radius decreases due to an increase in ZF. So if it loses an electron, that means it's... No, it usually loses an outermost electron. Whoa, all right, let's do this. The cations are smaller than their parent ion, okay, because there's an increase in ZF. So ZF is a positive charge, right? Positive number. So if you lose an electron, that means your ZF is going to go up by 1. You lose 2 electrons, your ZF is going to go up by 2. Okay? Now, cations are smaller than their parent atoms. So let's look at this with calcium. This is our calculation. ZF, calcium's still 20. Okay? There's 18 electrons. It's a +2. If those 2 disappear, our outer electrons change, shielding changes. We have calcium +2. Okay, these are now the outermost electrons there. And instead of being 20 minus 18, it's now 20 minus 12. Whoa, changes quite a bit. It's a +8 ZF. So its size is going to go whoop, way down. Way down. Okay? So you move the electrons away, and then you look for the outermost subshell. And those are the outermost subshell, and these here are your core or your shielded electrons for ZF. Why isn't it +6? Because calcium still has 20 protons. So 20 protons minus 6, 7, 8, 9, 10, 11, 12 electrons in the shielded layer. Okay? So it has to do with the shielding. It's not just the losing of the electrons. You have to consider the shielding in the inside layer. So just saying, it's going to change a little bit because we lose an electron is not true. It changes a lot. A lot. changes. So this is why calcium is much, much smaller. I'm sorry, the ZF of calcium, pardon me, is smaller, much smaller than the ZF of calcium 2+, which means the sizes are going to be the opposite. Okay? The larger the ZF, the smaller the size. Smaller the ZF, the larger the size. So let's look at some of these. How different is this? Well, this one has a radius here of about 150. When it loses its electron, its radius goes to about half. It's half the size because that ZF increased so much. Yep, quite a drastic change. So ions are always going to be, positive ions, cations are always going to be smaller than their parent atom. So here's a good visual, very easy way to see. Here's our atoms, here's our ions. Ions are on the right. And you can see they're all much smaller than their original parent atom. Some are much smaller, and some are just a little smaller. And why would you think that would be? Yeah, it has to do with the amount of electrons lost and the ZF. So it deals with the ZF and the particular situation that element is in, and the number of protons it has in its core. So ionic radii for anions. So now if you're gaining electrons, what happens here? Radius increases due to crowding of more electrons into a subshell. So the radius increases inside because more electrons are put into the subshell. The additional repulsion between electrons forces them further from the nucleus because you've got more electrons in there, and you don't have those extra protons, right? So fluorine, for example, fluorine's only got 9 protons. If you add another electron to it, you'll have 10 electrons, but you'll still have 9 protons. So what happens is, instead of them getting closer, they repel each other, and they spread out. Because electrons and electrons are both negative. The anions are larger than their parent atom. We can see this here. Fluorine atom and fluoride. The difference here is about 75 up to about 140. Almost double, just like the lithium. So all of these ions are bigger. The anions are bigger, and the cations are smaller. Yes, sir?
So when we do chemical reaction, we don't observe the difference in volume.
Right. At the atomic level, the volume changes we see, especially if you're doing 2 elements coming together to form a cation and anion, like lithium and fluorine, we're able to add them together. The volume change that we see is not usually due to their molecular or atomic volume is changing, because lithium is going to get smaller and fluorine is going to get bigger. And so relatively speaking, you don't see that. If you were able to view a salt crystal, you would see that the cations are always small and the anions are always large. And they're always pictured that way, or shown that way. And this determines their crystal structure. So we see the evidence afterwards of how the structure arranges, how those anions and cations go together if you make the compound. The volume usually changes of gases, for example, when heat is produced, because the volume of the actual particles is usually negligible to the end of gas law. You do have intermolecular attractions and stuff like that, but you don't see these in reactions. But you do see these in interactions and how they connect together. So here are some ions. You can see over here, our lithium ion is bigger than our beryllium. As you go across the periodic table, the size gets smaller for most of these. Okay, but here you can see that these, again, larger in size, all of them are larger than their parents, but these numbers are a little bit less than these numbers. Okay? So there's not a predictable pattern. If you're just comparing cations to cations, just the left side, you could say it gets smaller as you go to the right. If you're just predicting anions, it gets what as you go to the right? Smaller. They both get smaller as you go to the right. Okay? So it's not an incredibly predictable pattern, but you do know that cations are always smaller than their original atoms, and anions are always larger than their original atoms. So lithium and fluorine, if they come together, fluorine's original atomic size is small, lithium's atomic size is large. Lithium loses that electron, fluorine size gets big and lithium size gets small, the lithium ion. Cation is always smaller than the atom from which it is formed. The anion is always larger than the atom from which it was formed. So, please rank the following isoelectronic series in order of decreasing size. Alright, solve this problem. What are you going to do? I don't want the answer, I just want to know how would you go about doing this? What would you need to find out first? Protons, right? Protons would help us, yeah? Where they're on the periodic table, very good. Periodic table will help us, yeah?
The number of electrons.
Number of electrons, very good. Yeah? Zeff, very good. Zeff. So, before you try to rank them, you can guess that they're ranking, but until you calculate the Zeff, you won't probably have enough information. You might be right in your prediction, but you may want to calculate a Zeff for each of them first, and that will allow you to get their answer. So, let's see what we've got here. For these four, the first one is the rubidium, +1. Rubidium 1+ is atomic number 37, minus the shielded electrons is 30, so Zeff is for +7. You would look at the electron configuration of rubidium. So, rubidium here, when it loses one electron, okay, it has 36 electrons, that's right. These 6 electrons here in the P shell, okay, are the outermost electrons. These 30 other ones are the innermost ones. The 37 comes from the protons, not the electrons. Okay, 36, all right. This number here, 30, is the number of shielded electrons, not the number of electrons. So, number of electrons total, if rubidium loses one, is 36. However, these 6 are in the outermost subshell. They are all in the 4p6 outermost subshell. So these 6 electrons, okay, are not shielding each other. All 30 of these inside are shielded electrons inside of the outermost electrons. Okay? Okay, strontium here has 38 protons, same number of shielded electrons. Selenium, wait a minute, it's got the same number of shielded electrons? Yep, because selenium is becoming like krypton in terms of the number of electrons. So you'll notice the only thing that's changing is the number of what? Protons. Protons is changing, the shielding is not changing. So when these become ions, the shielding is all the same because that's what krypton would normally feel, the 30 shielded electrons. Now that we have these values here, we have to rank them in order of decreasing size. So the largest one go first or smallest? Decreasing size, yes. Largest, very good. Decreasing size. So decreasing goes the tall people to the small people, right? The smartest to the no. No, I'm short. Yeah, okay, so yeah.
Why would bromide have the same number of shielding? Because it's like, isn't it closer?
Yeah, bromine, when it gains an electron, it now has 36 electrons. So when it gains an electron, that's bromide ion. So now it has 36 electrons. Since it has 36 electrons, the outside 6 are still not shielded, and the inside 30 are. So that last p subshell, those are considered the outside unshielded electrons. Yes? Yep. Yep. All the ions that become the same isoelectronic with a noble gas, all will have the same shielded electrons. Only thing it changes is the number of protons. So we can see the smallest one should be largest one, Se, Br, Rb, Sr. Sieber Arbiter. Yeah. Yeah. Okay. Rubidium loses 1 electron. So it goes from having, it originally has 37 electrons, it loses 1. So now it has 36 electrons. It has 36 electrons, so out of those 36, some have to be outside and some have to be shielded.
Oh, so the last 6.
So the last 6 are from the rubidium is 4p, 6, okay? And then the other 30 are inside or shielded. So those outside 6.
So if it didn't have the 1+, it would
Had
have
36, yes. And that's why its size would have been much larger, because it would have had a very small ZF. And that's why rubidium's got a really big size. But when it becomes an ion, its size decreases dramatically. It's still bigger than amines, but its size decreases dramatically. Now, the size of an element, the size of an atom, the size of an ion, all can affect what is called the ionization energy. Now, the ionization energy is the minimum energy required to remove the outermost electron from an isolated neutral atom in the gaseous state. So this is what I was talking about, trying to steal the $1,000 pen or the purse. Okay? If you go and travel anywhere outside of America, where do you keep your passport?
In a passport bag.
In a passport bag. And where's the passport bag? You just like hang it out here like this?
It's like right here.
You have to keep it under your shirt.
Yeah, you keep it under like multiple layers of clothing, and oftentimes it's in your midsection where you don't think people will touch you. And you'll notice if they do. You're like, whoa! Right? So if you keep it in a place and you keep it protected, it's in the inside, it's in the core. You don't want anybody taking that, okay? Believe me, it's really hard to get a passport when you don't have one. All right, now, this is true with money or anything else. So, same option is in place. Closer it is to the nucleus, it's going to be harder to remove because of that positive-negative interaction. So, how does ionization work? It's measured in kilojoules per mole. Okay, the equation for this is you have a gaseous atom. It loses an electron, it becomes a positive cation. Okay, this is the equation for the ionization of a particular atom. X is, again, not a real atom, just a particular one. Okay, this value is also abbreviated as delta H. Okay, the change in enthalpy. The I sub 1 means the first ionization energy. So removing the first electron. And then if you're removing a second one, it's going to be I sub what, probably? I sub 2. Okay? If we look at ionization energy versus increasing ionization, if we look at ionization energy in general here, the patterns we should be able to see is which element has the greatest ionization energy. Helium. Okay? It is really hard to take an electron from helium. Okay? And that has to do in part because of its noble gas structure but it also has to do with the fact that it does not want to lose an electron. Okay? Which one is easiest to lose an electron? It's cesium. So you need less energy because cesium is what compared to hydrogen? Much bigger. The electron's further away. There's shielding going on. The shielding is what makes it a little easier to take it. Okay. Now, cesium, the funny thing about it is, though, does cesium have more protons than hydrogen? Yeah, so it's got more positive, it's got more negative. But because of those shells and those energy levels, and because of the shielding, it's easier for it to be removed. It takes less energy. So here's the first ionization energies. Which ones have the highest ionization energy? Okay, and the lowest? Well, this kind of seems like the reverse of something we saw earlier, right? What did we see earlier that was reversed? Size? All right, so size and ionization energy seem to be pretty easy, right? One goes up, the other goes down. Why? Well, as the Zeff increases, Zeff again, yep, electrons are held with more force. So Zeff increases, the electrons are held with more force. As the attractive force increases, more energy is required to remove an electron. It's all Coulomb's law, the force of attraction between the positive nucleus and the electrons. Okay? So, this is Zeff. Again, the distance makes a difference, but it's the Zeff that shows the force difference, and it's the force difference that allows the electrons to be easier removed as they get larger. All right, so we've already done lab number 9, which is a good thing about that. Okay, we're going to take a brief break. During this break, you're more than welcome to go to the bathroom if you need to. In about 1 minute and 9 seconds, 1 minute and 9 seconds, I'm going to be giving you treats and explaining some science of a molecule. Yep. We'll be playing Battleship right after this short little break. I'm not right after, pardon me. We'll be playing Battleship at the end of the day, yes. So, about a 2-minute break. That's interesting. So, when the electron is removed from an atom, the repulsion among the remaining electrons decreases. So you got less electrons repelling one another. So when you remove one, you got less that are repelling. And if we can get this to work, there we go. Come on. More energy is required to remove subsequent electrons. So the first one to remove is usually the easiest one to remove, and then it's harder and harder in general to remove subsequent electrons. The first ionization energy is less than the second, and the second's less than the third, and the third will be less than the fourth, and so on and so forth. If you have aluminum gas and it wants to become an aluminum plus 1, you want to lose 1 electron. The energy for this is 580 kilojoules per mole. Is the energy for the second one going to be greater or less? Greater. Is it a lot greater? About 3 times greater. 3 times greater to remove that second electron. And let's look at the third one. Yeah, so if you're looking at it from different perspectives there, not quite double the second one and about 5 times the first one. Why is this? Why is there such a change in the amount of energy? This one only requires 580 to remove an electron. You're still removing the same electron. Why does it require so much more energy to remove just 1 electron? I mean, all you're doing is taking 1. I mean, really, what's the big deal? Just taking 1 electron, I mean, it's like stealing candy from a baby, right? No big deal, right? Why is it this way? So, please tell the person next to you why you think it's this way. Ready, set, go. Yeah.
Taking candy from a baby would prove that it was hard.
Yeah, I met them this summer. I don't know if I still have the pen. Comic-Con? Yeah, if I can find them. Nothing for me, fortunately. I can't do it anymore. They changed the rules this year. No. My wife paid for it. Yeah. But Mythbusters was way cool. All right. So why does this happen with aluminum? Let's look at aluminum. Hey, here's an orbital diagram of aluminum. How many electrons does aluminum have in the 3p? 1. How many in 3s? And 2. So, try to take 1 away, it's in the 3p. The Zf right now would be 13 minus 12. Okay, so it's got a plus 1 Zf based on its position here. When you remove that 1 electron, now when you remove the second electron, the Zf changes to 13 minus 10. 13 minus 10. Now why is that? Because, boom, these are the outside now. So it changes dramatically. The Zf goes up to plus 3. When the Zf goes up to plus 3, what do we know about the size? Zf goes up, size goes down. So here we've got a Zf. When it loses this 1 electron, we will lose it. Low Chen is just a little behind. Okay? So the second one, the Zf, right now, if we lose 1 more electron, is plus 3. Okay, and the energy is much greater because the Zf, again, increases. Now, the next one isn't quite as dramatic of a change because, again, it's a plus 3 again. It's a plus 3, so this is a plus 3, that's a plus 3. It's not as dramatic of a change. Okay, again, it's still a large amount difference, but the big difference was between I1 and I2 because of the what? The Zf, the shielding, the shielding, the shielding, the shielding, the shielding, the shielding. So why is I3 greater than I2 even though the Zf is the same? No, the Zf is the same. More positive compared to the number of electrons? Okay. Very good. Electron pair repulsion. So the electron pair repulsion, if you have 2 electrons, like this, okay, these electrons repel one another. Okay, they're both negatively charged, even if they're spinning opposite directions. So, the second electron is easier to remove than the first. I'm sorry, not easier. Easier to remove than the third, pardon me. The third one no longer feels that repulsion from the one that used to be hanging out in the 3s. When it doesn't feel that repulsion, again, the value here is going to be a greater amount of energy for E3 because it doesn't feel that repulsion. So that is why these two are not the same, because this one feels repulsion. When it gets removed, this one does not feel the repulsion anymore. So that's why it's easier to remove this one because it's getting pushed out of there already. This electron is saying, hey, get out of here, get out of here, get out of here, get out of here, get out. And so then it leaves because it's being pushed around. No, it's being repelled by that electron. What about I4? Let's try to remove another electron from aluminum. Zf, 13 minus 4 plus 9. 11,575 kilojoules per volt. That's, 10 times the I2. I mean, that's it. Huge number. Since this number is so big, do you think something like this would happen under normal conditions? No, not very often. You got to have a ton of energy added in order for that to occur. That's why we don't see Al4+. Very good. Now, if you look at this graph, what do you notice with all of the elements?
As they go to the right,
Okay.
as they go to the left, to the right.
As you, all right, ionization energy increases. What do you notice as you go down and go from the blue to the red?
It increases, then it takes a giant drop.
Okay, takes a giant leap. Very good. Giant leap, giant leap, giant leap. Each of these giant leaps is when you're trying to remove one of those electrons from the p orbital.
So it's not what you find.
So you find it, yeah, you find it in nature where it doesn't want to lose that one. That one doesn't want to be removed because the energy is not favorable. Ionization increases always as you pull off more electrons. So as you pull off more, it requires more energy to remove more electrons. The ionization energies take a huge leap when we try to remove an electron from a new inner shell, especially a p shell. And Zeff, as you guys saw, increases dramatically. Okay? So for aluminum, why is I4 greater than I3? Okay, the answer is aluminum 3+ has a stable electron configuration, and thus more energy is required to remove the fourth electron. That's wrong. So why is I4 greater than I3? Tell the person next to you what you think. Ready, set, go. All right, why? Answers? One person, yes, sir?
The number of shielded electrons dropped a bunch because the outermost electrons are now the p orbital, which has 6 in it. So Zeff increases by a bunch, and so the size decreases by a bunch, and the attraction force is much bigger.
Very good.
Yay! And the balloon's smaller.
And the balloon is small. Very good. So all of those statements you said agree with the model of Zeff. Okay? The model in regular chemistry, or in other classes you might have heard, is it's stable, it's happy, it fits in like a noble gas. Well, maybe it is happy that way. That's the way it's found in nature. That's what we see in nature. But the reason for it has to do with the electrostatic interactions of the protons and electrons. The Zeff. Now, the Zeff again, is that completely made up too? Absolutely. Okay? I mean, it's totally made up, so we can get a measurement, a way to count it up and go, yes, I know that is true, based on the data, and then you look at the data and go, yep, that agrees with my observation. Yeah. At least it's theory. All right. So, if we look here, sodium and magnesium. Okay, in sodium and magnesium, we can see what is the lowest in their ionization energies? First one. First one, then second one, whoa, and then third one is way different for magnesium. Sodium, the first one is small, then there's a big jump.
That's why you have Na1+, and not
Yep.
2+.
Yep, Na1+, and what would Mg be? Mg2+. Now, there are some exceptions though. Okay, 1, N versus O and P versus S. If you look at this, as you go across the atomic numbers, the ionization tends to increase as you go across a row. But N and O does not work. Okay? For N, it has a higher ionization energy than for O. And P and S are exactly the same. The question is, what's going on with the N, the O, the P, and the S?
No.
For N and O has a greater ionization energy than N. That's what we would expect. The reality is just the opposite. So why is that? What's the deal with N versus O? So here's N, 2p3. Here's O, 2p4. You got 2 electrons. So what are they doing? repelling. Ah, so they're repelling one another. So if they're repelling one another, it takes what energy? Less energy. Electron pair repulsion. Less energy required to remove the first electron. Oh my goodness, that's awesome. So this electron configuration stuff actually helps us. That's cool. Without electron repulsion, I2 obeys the periodic trend. Okay? So for nitrogen and oxygen, again, if this was N plus 1 and O plus 1, okay, and then the P and S, okay, the P and S is for the same reason. It has to do with electron pair repulsion. Another exception is BE versus B. You can see it right here. We expect it to be going up like this, but it's not. And Mg and Al, that's a big drop, big drop. They both do the big drop at the same time. That's kind of weird. The N and O and the P and S did the same drop. So it must have to do with the electron configuration. Here's BE, here's B. Zf for the top one, 4 minus 2 is plus 2. For the bottom one, 5 minus 4 is plus 1. So BE has a greater Zf than B. Lower the Zf, lower the ionization energy. So boron has a lower ionization energy because it has a lower Zf. Now, this explains why electrons are removed and how much energy is needed to remove electrons. The opposite side of that would be what's called electron affinity. E sub A, or not E sub A, EA, pardon me. The electron change that occurs when an electron is added to an atom or ion in the gaseous state. So now we're going the opposite way. We're adding an electron to an atom in the gaseous state. So the equation looks very similar, kilojoules per mole. Frequency costs nothing, but actuality yields energy, therefore E sub A's are usually exothermic. The delta H is negative because Xg is less stable. It's at a higher potential energy than X minus, which is at a lower potential energy. So these tend to be, the oxygen is unstable, and it tends to want to gain electrons to become oxide. This is less unstable. Is it stable yet, though? No, it's O minus. What does that become to become more stable? O2 minus. Okay, so we can look at the next step. The next step for this electron affinity. Fluorine is very unstable, but when it becomes fluoride, it becomes very stable, and it actually produces energy in this reaction as well. It's an exothermic reaction. So you're producing energy when you add electrons in general. The electron affinity, when you're removing the electrons, you have to add energy. They're opposite processes. So E sub A of fluorine is much greater than the E sub A of oxygen because of this stability. If it was still unstable, it may not be as great of an energy change. So if we look here, this is called the electron affinity. As you go across the periodic table, okay, you can see that electron affinity increases. Okay, it becomes more negative as you go across in general. Okay, and as you go up, it becomes more negative in general. Okay, you've got some unique things happening here. Here's the general pattern of electron affinity. Not quite as clear in terms of the pattern, but you can still see that you have noble gases down here at the bottom. Okay, helium. But you also have other elements down at the bottom besides noble gases.
Wait, what's AT?
AT, astatine. Number 85 on the periodic table right there. And AU is gold, yeah. So, you can see here, the interesting thing is F, Cl, Br, I, and AT are all in what group on the periodic table? They're all grouped in the halogens here. They're all group 7. Okay? Gold is not, though.
Gold is special.
Gold is special, so of course it's got to be in.
People
Yeah.
like the gold.
All right.
It got wrinkly. Oh, it got crispy.
Got crispy and cold. All right. So for the next experiment,
Oh, big one. Oh, they are?
use the liquid oxygen.
On your foot. Oh, really? Feeling a little yellow, you guys.
All right. What I'm going to show you now is liquid oxygen. You take this out here. See? All gone. Gone. Too fast. It was liquid, yep. Freeze chocolate? No. Did you drink that? Not at that temperature. It would freeze you. I'm sorry, I probably should have told you to pay careful attention to see the liquid oxygen. It's hard to see. All right. Now, the next relationship we're going to look at is what is called electronegativity. Electronegativity is one of the most important periodic table trends you'll see. I apologize that it's last and it's almost at the end of the day. So, right before Thanksgiving. So, the cool thing about electronegativity, though, is it's the ability of an atom to attract pairs of electrons towards itself in a covalent bond. It is a property of an atom in a molecule. So if you have two atoms, like hydrogen and oxygen, oxygen and hydrogen, when they connect together, they make a molecule that looks like this, called H2O. The O and the H are not the same element, so they don't attract electrons the same way. They have a different electronegativity. One attracts the electrons more than the other when they're sharing. So it's what I like to call unequal sharing. Hey, if you have a brother or sister, you may know this. My older brother, 5 years older, would take me to go get ice cream. He'd get money from my mom, we'd drive there, he'd get me ice cream. He'd get a double scoop of ice cream for himself, and he'd say, "You're sharing." He would eat it, and I would be reaching up trying to grab it for the next 10 minutes. I get to hold the cone. Sometimes he would ask me, "Here, you want a lick?" And he would go, pull it away.
Wait, how can you do that if you're holding the cone?
I was 5 years younger than him. I was a lot smaller than him. He was much stronger than I was. Not anymore. But this is how I remember electronegativity. It's my brother got a higher electronegativity. If the ice cream cone represented those electrons on the cone, he was pulling them towards himself, closer to him than me. Okay? I really wasn't getting much of anything. But that's only when it's sharing. If I wasn't sharing, it would be called an ionic connection. He would just run away with it. I'd run after him. Because he would have the ice cream, which is the electrons, and I'd want the ice cream. So I would lose the ice cream, so to speak. I'd be positively charged, he'd be negatively charged. I'd run after him. I'd stick to him.
He's the bad guy. This is negative.
Yes, he is the bad guy. Absolutely. Thank you. All right. So, that's just an analogy. We will use that later. But electronegativity takes into account atomic radius, mass, and electron affinity. The electron greed. I don't usually say my brother's greed, but electron greed. The higher the electronegativity, the more greedy an atom is. The atom with the higher electronegativity will pull shared electrons closer to itself. So, older brother pulls them closer to himself if the electrons are the ice cream scoops. This was first proposed by Linus Pauling in 1932 as a development of valence bond theory. The Pauling scale of electronegativity ranges from 0.7 for francium to 4 for fluorine. So, which is the biggest out of these two? 0.7 or 4? 4. So francium or fluorine, which would win? Fluorine. Fluorine's the bully on the periodic table. Okay? I don't usually think of fluorine as my brother, but sometimes it works for me. Francium, well, unfortunately, France has an interesting, how can I say, people, not to offend anyone from France, but for some reason Americans think the French are really weak. Yeah, some people think they really, well, some people have different views of the French. Now, I only think of this because of France saying, white flag, I surrender, I surrender, I surrender. But francium happens to be found in France, and it just happens to have the lowest electronegativity on the periodic table. Just as a coincidence. I don't know why. Yeah. Yes, my wife is French. She's not weak. All right. Electronegativity determines the bond polarity. So the differences in electronegativity determine the bond polarity. In a molecular formula, the element with the lowest electronegativity is written first. That's why when we write NaCl, what's written first? Na and then Cl. Because Na has a smaller electronegativity than Cl. What happens in NaCl is the Na gives up the electron, the Cl takes it. It's an ionic bond. Okay. Except H in acids, which H in acids always messes things up. So the electronegativity increases as you go across the periodic table and increases as you go up. So this is the electronegativity scale. Now, these gases here, hydrogen, all of these here, all the halogens, these are all gases. So except for carbon, 1, 2, 3, 4, 5, 6, 7. Those are our what at 7? 7 at 7, not the scary ones, but the 7 at 7. Carbon is not, but these atoms here, those atoms here, all tend to be gases with the exception of the bromine and iodine. Okay? Now, learning these here, the general trend, you could memorize these numbers. It says learn these, not memorize. So what I do is I look at it and go, okay, which one's the greatest? Fluorine. This one's the smallest. It goes diagonal across. Right? That's the general pattern. Once you see the general pattern, that should be able to explain most things. There are some weird things, like N and Cl have the same electronegativity. Pretty strange. But that means if they were connected together, one N, one Cl, if that was possible, they would share almost equally. But if you remember the general pattern, that works out great for electronegativity. So here's a summary of the periodic table. Yes? Francium, yeah, you got kicked off of that one. This one only went up to row 6. So, not the best picture in the world, I agree. I know, francium.
It was barely cut off.
Yeah, the whole row got cut off. So, these are all the trends we saw in the summary of the periodic table. Ionization energy goes up as you go across. Electron affinity goes up as you go across. Atomic radius goes down as you go from right to left. Atomic radius goes up as you go from top to bottom. Ionization energy goes up as you go from the bottom to the top, and electron affinity goes up. Now, another characteristic is called the metallic character. Non-metallic character. You can even think of that, it's the same as electronegativity. The more non-metallic, the more electronegative. The more metallic, the less electronegative. It's a general pattern that fits with electronegativity. Okay? I don't usually refer to these two, but that is the general trend on the periodic table between the francium being the most metallic and the fluorine being the least metallic in general on the table. So, as you go from left to right, what increases? Okay. So, the AR and the IR decrease as you go left to right. And the IE, EA, and EN increases as you go from left to right and top to bottom in the ZF. So those are the general patterns we saw. So, random holes, that's called sodium. When sodium reacts with water, it can explode. Alright, now, I know you guys are ready to leave, so I've got one fun demonstration for those that want to stay. We're going to go outside for this one. Yes. So you're more than welcome to outside. What's up? You can keep your balloons. Yeah, you can take all your stuff with you. We are going to do one demo with liquid nitrogen before we leave. It's a pretty fun one. How long will it take? It'll take a very, very short amount of time. It's about as long as it takes people to get outside. daily quizzes are something that we have first quarter only, and they
What is the actual score? I mean, I don't know how she did in the finals. I didn't get anything.
it's all on Learning Point. So if we look on Learning Point, I'll show you how to access
yeah, we
the
are
actual
accessing
grade.
it, but this is the only thing that's showing up.
So let me show you how to fix that. Hopefully there's not a problem with Learning Point, which has happened. So, alright, having problems opening a website. Alright, so Learning Point. Alright, why is that? Alright. So, can you enter in your username and password? Because sometimes I can see things that for some reason don't appear. We've had the new Learning Point shouldn't cause a problem, but I can show you where it is on here. So here we've got the grades here. So if you click on here, it's individual grades for quarter one. Okay. And so we've got for AP, it's a little different because you've got two different things. So we got chemistry period 1, chemistry period 2, and honors chemistry period 1, daily quiz. So that was what you saw. Hello, and then this is the honors chemistry 1 period 4. So this is the actual grade.
So period 4, okay.
So yeah, these are the same period. This is just the daily quiz one, and it said on the previous page. I tried to explain it because it's a little different for sure. For AP Chem, there are overall grades and daily quiz grades. So
Anita, are you getting it?
Yeah.
Okay.
so the daily quiz grades have been added into the overall grade. So the daily quiz, I should take that off because it's no longer pertinent, but it tells how you get the score you do, and then your student grid number. You put your grid number in
Can
here.
we have a look at it now,
Oh yeah,
if you don't mind?
you can put it in.
Because I don't know.
Nope, no problem. Yeah, that's why I wanted to show that to you. And so, her daily quiz scores, she got 80 out of 80, so she got 100% of the points for the daily quiz scores. So she got 100% in that second.